differentiate using the product rule, you should end up with that. So I've let u equal a to the e minus kt, which differentiates to minus ak e to the minus kt. All get that bit? And then let v equal sine 2 pi ft. The constant a here is the 2 pi f bit, so that comes outside, applies, change the function to cosine. Bring all that together, you end up with that lot. Okay, no real point in trying to simplify. We've been given some values. T equals 1, A equals 2, K equals 0.9, F equals 5. Plug those into that formula. So ds by dt is equal to I 2 times e to the minus 0.9 times 1, because t is 1, so we leave that, multiplied by 2 pi times 5 times the cosine of 2 pi times 5. T is 1, so we just leave that, plus, go on a new line for me, sine 2 pi times 5 minus a 2 times 0.9 e to the minus 0.9. Plug all of that in the calculator. You should get minus, sorry, not minus, equals 25.55. Says find the displacement in centimeters per second. So displacement's in centimeters, therefore the velocity must be in centimeters per second. Is that what you got when you plug those into your calculator? Yeah. All right. All happy with that example? Yeah? Need to practice that product rule. Right. Velocity and acceleration. When a car moves a distance x meters in time t seconds along a straight road, the velocity v is constant, then v is equal to x over t meters per second, i.e. the gradient distance time graph. Yep. So if we've got constant velocity, what we're looking at is that velocity is x over t. Change in t, change in x position divided by the change in t time. Yep. So if that's meters and that's seconds, we've got a velocity in meters per second. When the velocity is not constant, so a car, if its velocity is not constant, then the distance time graph will not be a straight line. Could be like it is shown there. However, I don't think that kind of velocity change could carry on for too much longer. It's going to tail off at some point. So, in the last slide, we saw that the slope of a distance time graph represented the velocity. So on the x-axis here we've got distance moved over time, and that's increasing its rate of change all the time. So if we take a point x and we take the tangent to it at that point, then that is the velocity at point x. So if an expression for the distance x is known in terms of time, then the velocity can be found by differentiating that expression. So we've got a function for position over time. We differentiate that function, we get the velocity. The acceleration of a car is defined as the rate of change of velocity. So velocity is the rate of change of position. Acceleration is the rate of change of velocity. We're getting so many meters per second faster every second. So we can find the slope of that curve by differentiating the function f of t, which is v. So if we differentiate velocity, we get acceleration. So if we know velocity in terms of time t, then we can differentiate that expression and get the acceleration in terms of time t. Alright? In summary, acceleration is dv by dt. However, v is dx by dt. So we're talking about the acceleration being differentiate position twice, or take the second differential, and that's written as d2x by dx squared. Effectively, the second differential of position is written like so. So if a body moves a distance, to summarise, x meters in time t seconds, distance x is a function of t, velocity is the first differential of that function, dx by dt, or that's the gradient of the distance time graph. Acceleration is dv by dt, or the second differential, d2x by dt squared. Gradient of the velocity time graph. Okay? Later on, a couple of weeks' time, we'll look at the reverse of this, where you can find the area under these curves and find out the distance moved, that kind of thing. Okay? So, angular displacement, theta radians of a flywheel, varies with time t seconds and follows the equation angular displacement theta equals 9 p squared minus 2 t cubed. We got to find A velocity and acceleration when t equals 1, and B time when beta is equal to 0. So, how do we find the velocity? V. From the last slide, how do we find velocity? d theta by dt. So we differentiate that function. So the differential of that, differentiating 18t minus 6t squared. Yeah. And we're doing A at the moment. When t is equal to 1, v is equal to 18 minus 1 squared is 1, so 18 minus 6 equals angular So that's radians per second. What's the golden rule regarding calculus and angle calculations from last week? Anyone angles must be in radians, yeah? We can always convert it to degrees per second if we really want to know that, but to do the calculus we must have them in, we're using cosine or sine, we must have them in radians. Okay? Acceleration is equal to d2 theta by dt squared, the second differential. So you've got to differentiate that function. Yeah? Differentiate 18t differentiate minus 6t squared t. When t equals 1, a is equal to 18 minus 12 equals 6 radians per second squared. Okay with that so far? So we've differentiated once to find the velocity. So differentiate position once to find velocity, expression for velocity. Differentiate a second time to find an expression for acceleration. And the last bit is we want to find when the angular, so B, find when A is equal to 0. So we simply set the second differential find when the angular acceleration is equal to 0. The 18 minus 12t. So we say 18 minus 12t is equal to 0. We rearrange that. (18) equals 12t. T is equal to 18 over 12 equals 1.5 seconds. Okay, we're finding turning points. In the diagram below, curve has two turning points. So this is similar to the one we looked at earlier last week at P and Q, where the slope of the curve is 0, and hence the differential of function dy by dx is equal to 0. So point P is a turning point that's maximum, and point Q is a turning point that's minimum. So when we want to find these turning points, we may or may not want to know not only is it a turning point, but what nature is it? Is it a maximum or a minimum? We can do that. There's two ways that we can solve that problem. We can look at we can find a value, we can find a function for the gradient, dy by dx, and we can set that equal to 0 and find a point for x where dy by dx is equal to 0. Then if we look either side, a maximum, so if we go either side of that x point, so let's say we find that x is equal to 2, if we look at x is equal to 1.5, and we look at x is equal to 2.5, and we find a negative slope, we know that that turning point is a maximum. We have to be careful about how far either side we look, because we need to be careful we don't go either side of another turning point. So we need to bear in mind what kind of scale we've got for x. If that's really small and we need to move a small amount, if it's really big and we can move a bigger amount without too much worry. If however we find we're looking either side of x and we get a negative slope before and a positive one after, that turning point must be a minimum. So it's about finding a function dy by dx, finding out where that's equal to 0, and then looking slightly either side to find out whether that's a minimum or a maximum. We can also have, as well as minimum and maximums, what's called a point of inflection. And here we've got a 0 dy by dx, and either side of that point are negative slopes. So there's a point of inflection that way. And on this one, either side of that point, we've got slopes that are both positive. So there's two types of point of inflection as well that we could come across. But they're not going to happen in quadratics, but they're happening possibly from cubic equations upwards. You can get points of inflection as well. Yeah. So, procedure for finding and distinguishing between turning points. First, find the x and y values at a given turning point. So we find the point where dy by dx is equal to 0. Okay, and solve for the values of x. Substitute the value of x into the original equation to find the corresponding y value. So this is establishing where that turning point is on the graph. And then there's two options to determine the nature of whether that's a minimum, a maximum, or a point of inflection. We can determine the gradient either side, just before and after, as I just described. And then if it goes from positive to negative, it's a maximum. If it goes from negative to positive, it's a minimum. And if it's positive to positive or negative to negative, it's a point of inflection. Or, and sometimes an easier method, is to find the second differential and substitute it into it the value of x found when dy by dx is equal to 0. So substitute that value of x in, alright, and if the result is positive, the point is a minimum. If it's negative, it's the maximum, and if it's 0, it's a point of inflection. However, that method relies on you being able to find the second differential. In that previous problem we looked at, the one on angular velocity and acceleration and so on, finding the second differential was relatively easy. However, when you've done the problem earlier, product rule 1, would you like to try and find the second that on a piece of paper? Probably not. You'd look either side and look for positive slope, negative slope, or negative slope, positive slope, or both the same. Alright? So it just depends on what The problem is, and what the function is like, as to which method you would choose there, because there's a possibility that finding the second differential is a step further and you really want to go without making mistakes. Okay? Well, look, we got an example. Find the maximum and minimum values of the curve y is equal to x cubed minus 3x plus 5. First by examining the gradient on either side, and second by determining the sign of the second derivative. So how are we going to tackle that? I think we'll do this one together. What do you reckon? What we got to do? Yep. You are by dx is equal to x, yeah, minus that's 3x squared, yeah. What type of equation? Yeah, quadratic. So it's going to have either one or two, a graph here. Is a either 1, 2 or no values of x. What methods do you know to solve the quadratic equation? So we've got to say 3x squared minus 3 is equal to 0. Formula method? Use the formula method? Can you remember the formula method? Minus b plus or minus square root b squared minus 4ac 2a. In this case, what does a equal? B sure. Quadratics in the form of ax squared plus bx plus c. B is no x term, so b must be, yeah, and c minus 3. So we got is equal to minus none plus or minus square root of none minus 4 I 4 times 3 all over 6. Over 2. What's the square root of 36 equal to? Sure? What other number multiplied by itself is equal to 36? Plus or minus 6. So it's plus or minus 6 over 6. X is equal to 1. X is equal to minus 1. Two values. Happy with that? Or not? I mean, maybe you might have been able to see that a bit easier than that and done factorization rather than the formula method. But anyway, we've got our two values of x where the differential is equal to 0. So we've found 2 points that are either minimums or maximums. So a function is yep. So what we've got to do now is have a look at using this method, we've got to examine the gradient either side of the turning point. So when x is equal to 1.1, dy by dx is equal to that'll cover the turning point at x equals 1. You need to find or negative, remember, and nature. Dx was equal to 3x squared minus 3. So this is 3 times 1.1 squared minus 3 equals 3 times 0.9 squared minus 3 equals 3 times minus 0.9. Be careful with that. You need to bracket that term before you square it on your calculator. Yeah. Minus 3 and 3 times minus 1.1 all squared minus 3. What we got? This one? Sorry? 0.63 and the 0.9 squared one? Negative. From a negative slope before to a positive slope after. Minimum or maximum? Yeah? Let's just move that. And put in here, change from negative to positive, therefore x equals 1. There is a maximum. Yep. Plug them in your calculator. What do you get? Remember, that one's before and that one's after. Because we're going from a negative number. So this is the before and that's the after one. What we got now? Minus 0.57, 0.63. Yeah? And this one's before. And this one's after. So we've got a positive slope before. That's negative slope before. We got that wrong. That's a minimum. Negative slope before is a minimum. That one's the max. Point 0.9 as before, negative, slopes that way. After positive, slopes that way. So we must have a minimum. And after six three. Sorry, Lewis. Slightest touch on the board makes a mark, as you know. Okay. So, alternatively, you can have a look at this yourselves. You can use the other method. So you can find the second differential. So that's the first differential. Second differential is 6x. Equals to 1. Using those rules we talked about earlier, using the second differential. Have it gone? positive indicates a minimum at x is equal to when x is equal to. The other, of course, is either sketch stop there. There are some other problems in your notes. I'm not going to linger on them. They're there with solutions, not necessarily work solutions, but usually the answer. They come out of the Bird book, so there are things that you can have a practice at. Okay, if you really want a solution at some point, then it might be possible for me to produce something. Next week we'll move on to recap on integrity.